population. Did I mention what it is? Sigma is equal to 3. The sample size is equal to 9. So I'm going to put that in here. Sample size is 9. Whoops, 9. Sigma, standard deviation of the population, is equal to 3. Okay, so let's figure out what the 95% confidence interval would be for the population that I drew this sample of 9 randomly chosen individuals from. I'm not going to make up a story behind these numbers. I'm just going to work with the numbers. Okay, you guys can build your own study around it. Okay, so let's figure this out. The mean of this, I'm going to call it X bar, since it's the mean of the sample, is equal to the average of these 9 numbers. Okay, there's the average of those 9 numbers. Okay, so now if I want to calculate the standard error, how do I calculate standard error? Standard error is going to be equal to, what is it going to be equal to? It's going to be equal to the standard deviation sigma over the square root of the sample size. Right, so that's going to be equal to, it's going to be equal to 3 divided by the square root of 9, which is 3. So that's going to be equal to 1. Standard error is going to be equal to 1. So if I'm going to build my confidence interval, a 95% confidence interval, okay, what is it going to be equal to? What's the lower value for my confidence interval going to be equal to? It's going to be equal to my mean, right? Mean, which is, where did I put the mean? Mean, which was here, minus the standard error, which is 1, times what value? 1.96. Great, perfect, right? Because it's the z-score, right? And for the upper value, it's going to be equal to the mean plus 1.96 times my standard error. Okay, so that's my 95% confidence interval. So if I looked at this, the value that I'm comparing it to, the mean of the other population I'm comparing it to, is equal to 8. So does this confidence interval include 8? Yes. Yeah, it does. So can I reject the idea that the means of these two groups, two populations, could be the same? Can I reject that idea? No, I can't, right? Because it could be 8. 8 is inside my 95% confidence interval. If I'm saying that the mean of the population for group A, which I took the sample from, is between 7.9 and 11.8. And I know that the mean for group B is 8. Well, I can't say with 95% certainty that the mean for group A is not 8, right? Because that's my confidence interval. That would be conceivable within that level of certainty, right? So in order for me to say that the means of these two groups are different, well, how about 7? Would I be able to say it if it were 7? Yeah, 7's outside of the confidence interval, so yeah, I could say that they're different, right? Get it? In other words, if I'm 95% sure the mean for population A is between 7.9 and 11, right? I'm 95% sure it's between those two numbers. If I'm comparing it to another population that has a known mean of 7, I can say I'm pretty sure that it's not going to be the same. The two populations are not going to have the same mean, right? But if the number were 10, right, well, that's inside my confidence interval. I don't know for sure that the two populations are different then, or at least my version of sure is 95% certain. So I'm going to do this a different way now. I'm going to use a t-test. Okay, and the way I'm going to do that is I'm going to say to myself, well, how do we calculate a t-score? In this case, our t-score is going to be for basically the same as we would do it for a large sample because we know sigma. So it's really going to be a z-score, right? So our z-score is going to be equal to, it's going to be equal to what? Well, let me put it over here first. It's going to be equal to x bar minus mu, the difference between the two means, divided by the standard error. Okay, so let's figure out what our z-score is going to be. Z-score is going to be, I'm going to go back to the number 7, which we started with. I'm going to change that to 7. So our z-score is going to be equal to 7 minus, excuse me, went a little bit backwards there. 9x bar minus, Every time I click in the wrong box here, I wound up having to rewrite this. Okay, it's going to be equal to x bar minus the mean I'm comparing it to, right? I'm looking for the difference between the two means, see how many standard errors apart they are. And the standard error is equal to 1. So let's see what z-score is going to come out to be. The z-score comes out to, did I make a mistake there? Oh yeah, I actually, tell you the truth, it was 8, wasn't it? Yeah, I started with 8. Let me go back in there and change that to 8. Oh, I can actually change it in here, I think, if I referenced it. Okay, the z-score is 1.88. Is that a z-score that tells you that that's outside of 95% of likely outcomes? What z-score would you get? What z-score would give you an outcome that would be likely to occur less than 5% of the time? 2.5% on the low end, 2.5% on the high end. What would that z-score be that represents 95% of the outcomes? 1.96, right? So is this bigger than 1.96? It's not, it's smaller, right? So we don't have a big enough z-score to say that we would get this, we would get this result more than less than 5% of the time if the two populations were different. Okay, so we can't reject the null hypothesis because our z-score is not big enough. Let's do the same thing now, except we're going to do like we might find it in real life. And for instance, if I had said 7, remember 7 is outside the confidence interval? If I had said 7, notice my z-score is big enough now to reject the null hypothesis. All right, so now we're going to do this a little bit more formally also. I'm going to look at, okay, here's our numbers.
What would you use Excel for confidence interval?
Confidence interval, I calculated it, right? I'm going to click back in here. I used the difference between I actually calculated x bar minus mu, I'm sorry, excuse me, x bar minus 1.96 times the standard error, right? I'll write that out. Confidence at x bar minus 1.96 times the standard error. Okay, makes sense. Just as we've done it before. Now this time, I'm going to clear all this out. Okay, I'm going to do this again. Except this time, I'm going to go back here. I'm going to use the same numbers as I used before. And I'm going to also test it against the mean equal to 8. Right? Actually, I might even, let me change that. I'm going to change that to the 7. Because 7 worked for us before, right? We were able to reject the null hypothesis at 7. I'm going to try it again I'm going to compare it to a mean of 7. So what do I know here? Single sample t-test. I know the mean of a population that I want to compare this to. I don't know the mean of my test population. So what I'm going to do is I'm going to take a sample of 9 people from my test population. I'm going to find the average, and then I'm going to compare it to the mean of a known population that I want to decide whether it's the same as or different from. Okay, so in this case, I don't know what sigma is. Sigma is unknown, right? So the only way I can predict the variability in the population of the group that I'm actually taking a sample from is by calculating the standard deviation instead of having sigma. So I'm going to go back here. Same group of numbers we had before, okay, except this time I don't know sigma. I'm calculating the standard deviation. Sample size is 9. What's the standard deviation equal to? Standard deviation of these 9 numbers is 2.93. Okay, so now what's the average? The average is equal to, right, should get the same numbers before. And what's my standard error equal to? My standard error is equal to, let's see, it's going to be equal to the standard deviation divided by the square root of the sample size, which is 3. 9 square root of 9 is 3. So my standard error is 0.97, roughly the same as I got before, right? Not much different. Okay, so now when I calculate my confidence interval, because I don't know my mean, my sigma, I don't know the population standard deviation, I can't use 1.96 anymore. I got to use the t-score, right? So let's calculate our confidence interval. Confidence interval, again, I'll write it up here, is equal to x bar plus or minus, x bar, not x bar, plus or minus the t-score for a 95% confidence interval times the standard error, okay, instead of z. So what's that going to be equal to? It's going to be equal to, let's see, the mean is 9.88 minus, well, what am I going to use for the t-score? Anybody look that up already? Let's get the table up. Let's see, I got it in here. Sample size is 9. How many degrees of freedom is that? Oops, I got the wrong one. Okay. Okay, sample size is 9. Degrees of freedom is equal to 8. So 95% confidence interval, we're going to be using 2.3. Okay, 2.306. I'm going to use 2.3 for our purposes. Okay, so that's going to be equal to 2.3 times the standard error, which is roughly 1 again. Okay, this time it comes out to be 7.6. Remember what it was the last time? It's like about 7.9, right? Okay, so it's wider. Why is it wider? Because we're using t instead of z, that 1.96. We've increased our level of uncertainty. And that t-score, the bigger the sample size is, the closer and closer it gets to 1.96. So the less uncertainty I have about the variability. So what's the z-score on the other end? It's equal to x bar plus 2.3 times the standard error. Okay, so our 95% confidence interval for the true mean of population A is between 7.6 and 12. So if I'm comparing it to a population that has a mean equal to 8, can I say that they're different, those two means for those two populations? Let me move that up. See, I can see you guys squinting at that. Can I say that they're different? As a matter of fact, let me do something else. How's that? Can I say that those two populations are different? Right? The mean of this population I know is 8. What's the mean of this population? We're 95% sure it's between those two numbers, right? Could it be 8? Could it be the same as this population? Yeah, it could, because it could be within that range anywhere, right? We're not sure, with 95% certainty, we're not sure where it is in there, right? So I can't say that they're different. In order for me to say that they're different, I have to be comparing it to a number which is outside that range. Can I say that they're different now? Yes, because we have that mean is outside that confidence interval. Again, we only do this with a single sample t-test, right? We don't compare. If I had two samples, I wouldn't know either mean, right? I would only know the confidence intervals. So I would not trust comparing the two, seeing if they overlap or not, right? But this I can. Now, what if I want to do this in the form of a t-test? What would be the t-value? How many standard errors apart are these two means that I want to compare? Okay, how do I calculate the t-value? What is it equal to again? It's equal to x bar minus mu divided by the standard error. So what is t equal to in this case? Whoops. Let me do that again. Equals x bar minus mu over the standard error. I'm not putting parentheses in there for now. So what's the difference between x bar and mu? Well, x bar is 9.8 minus mu, the thing I'm comparing it to, which I do 8 or not, 8 or 7. What do you think? What's going to happen if I do 7? I'm going to reject the null hypothesis, right? I'll give it a try. Okay, divided by standard error is equal to 0.97. So what does t come out to be? 2.95. Can I reject the null hypothesis? Can I say with that big a t-value that I can reject the null hypothesis, right? What value of t do I have to exceed to reject the null hypothesis? 2.3, right? Exactly. Not 1.96, but 2.3 is dependent on the sample size, right? Good. And what would happen now if I did it again, except this time I compared it to 8 instead? What's going to happen? Okay, you should know enough now to predict what's going to happen here, right? Minus 8 over the standard error. Let me put this in parentheses. Over the standard error, which is 1. What's going to happen now? Am I going to be more than 2.3 or less than 2.3? Oops, did I make a mistake there? Wait a second. Let me do this again. Equals 9.8. But let me put parentheses in first. 9.8 minus 7, close parentheses, over the standard error. Enter. 8. You're right. Yeah, I meant to put 8. Okay, do I exceed 2.3 now? No, I don't. So I don't reject the null hypothesis.